Let's begin. Hello, everyone. This is Tanya. I'm one of the TAs assigned to the aircraft design course taught by Professor A.K. Ghosh. So let's start with the contents of this week. You remember we had discussed this question, why anhedral? Why an anhedral angle on high wing aircraft? So were you able to find out why? We saw that the high wing configuration is more stable laterally and the low wing configuration is less. We introduced a dihedral angle into the low wing configuration to increase the lateral stability. Someone had asked a question that when we have high wing aircrafts, we also see an anhedral configuration. Why? First of all, where is the anhedral seen? What types of aircraft? What missions do they accomplish?
High wing,
Sorry?
cargo maybe.
Cargo, yes, cargo is one. Cargo and fighter jets, right? Fighter jets that have high wing configuration also have a slight anhedral angle. Can someone try to why this anhedral is introduced? To improve lateral stability. What about anhedral? So, let me just draw this. So we had low wing configurations that were not laterally stable. So we introduced a dihedral angle. So this angle is called dihedral. But high wing aircrafts, high wing configurations are stable. And now we see that most of the high wing aircrafts that are seen, for example, in cargo and fighter jets, have a downward bend. So it has an anhedral angle, right? Compared to the local horizontal, it has an anhedral angle. I think it's represented by the same angle, just negative. So can someone try to tell me why this anhedral is there? Just try to reason, right? This is laterally unstable. This is laterally stable. This is laterally stable. What would this be?
They're introduced for more longitudinal stability.
Okay, we introduced a dihedral for longitudinal stability. What about anhedral is also for stability?
Yeah, can be.
Okay. Okay. So it is actually the reverse. Okay. So high wing and dihedral both introduce roll stability. So for a high wing configuration, like in cargo aircrafts and fighter jets, it is already very stable in the roll configuration. Do not introduce this anhedral, it becomes difficult to control. So when it is more stable, it is less controllable or less maneuverable. So for fighter jets especially, we do not require it to be as stable as for the passenger aircrafts. So we need to introduce some, not, you can't really say instability, but it contributes towards helping in the roll control. So it does not, this anhedral angle does not tend to bring the aircraft back to the equilibrium condition when it is rolled to the left or right. Okay, similarly, for cargo aircrafts, it is very heavy at the bottom. So it, by virtue of its weight that is below the CG, it will below the point of lift generation, it will tend to bring the aircraft back to its equilibrium state when rolled to the left or the right. So it is more stable than the low wing configuration. It has a high roll stability. So to introduce more controllability or maneuverability, we introduce an anhedral angle, right? So that is why the anhedral angle is introduced, and we see it in cargo and fighter jets to make it more controllable. This is more control. More controllable means less stable. So it does not have an initial tendency to come back to its equilibrium condition when it is rolled. Okay. So in the previous class, we had seen, previous or the one before that, we had seen what is adverse yaw. Does anyone remember what is adverse yaw? Not why it's caused, like just tell me what it is. What was adverse yaw?
Ma'am, it means the side roll movement due to gust of wind.
Okay. So adverse yaw was the yawing of the aircraft in the opposite direction to which we roll. So if it's rolling, this is your fuselage reference line. If it's, okay, I can't show it this way. If it rolls to the right, if this was your rolling moment, and it yaws in the opposite direction, that was the adverse yaw, right? It was due to the unequal distribution of the lift and the drag. So if it's rolling to the right, it yawed to the left. Am I right?
Yes, ma'am.
Yes. Okay. So similarly, for sake of completion, what is side slip introduced rolling moment? So when there was a rolling moment, you had a yaw introduced. So they are coupled motions, lateral and direction coupled motions. So if you have a side slip, there is an introduced rolling moment, right? What factors affect the rolling moment? What factors do you think affect the rolling moment? So if there is, this is your fuselage reference line, you have a positive side slip beta. This will tend, if for a stable aircraft, the aircraft will yaw towards this direction and it will negate the effects of the side slip. But it will also introduce a rolling moment, right? What factors do you think introduce the rolling moment? So when you roll to the right, it introduces the yawing moment, an adverse yaw. Rolling right causes a left yaw. Similarly, if you are yawing to the right, it introduces a rolling moment, right? What factors affect these rolling moment? Just try to reason it. So what makes, for a stable aircraft, when it is subject to a positive side slip, I just mentioned that it will yaw to the right to negate the effect of this positive side slip. What component of the aircraft causes this to happen?
Vertical stabilizer.
Vertical stabilizer, yes. Can you tell me why? So vertical stabilizer is something like,
Because it is a symmetrical airfoil, and due to side slip there induces an angle of attack which produces lift, I
yes.
think in the direction of perpendicular to the direction of the angle,
So there
side
is,
slip angle.
yes, exactly. So you have the vertical tail sees an angle of attack here, beta. It produces a side force. So there is an Fy, which, if this is your CG, it produces a restoring moment and it makes the aircraft turn in the direction of the side slip angle, thereby negating the side slip angle. Now, can you try to see what factor this Fy? This is a negative side force, right? This is negative because your positive y-axis is in this direction. This is positive y. So can you try to see from here, from this Fy generation, why it would cause the rolling moment? Just try. This is from the top view. Just draw the side view. Okay. So this is your vertical stabilizer, vertical tail, which causes a force in this direction, right? This is your negative Fy. Okay. So can you try to see how it would introduce a rolling moment?
Yes, ma'am, because it the force acting is if we take on aerodynamic center of the vertical fin, then it is above the CG,
Yes, yes,
and
exactly.
there is a movement arm.
Yes, there is the CG is somewhere here along the fuselage. So this force produces a rolling moment. Not sure how to represent that. If this is your x-axis, it produces a rolling moment in this direction, right? So this is one of the conditions where your vertical tail, if it's above the CG, if the aerodynamic center of the vertical tail, like he said, if it's above the CG, it has a moment arm. It has a moment arm which introduces, this is, so if this is some x distance, so the rolling moment would be Fy into x. Fy is negative. So introduces a negative rolling moment. Okay, this is one of the factors that introduces a rolling moment when the aircraft encounters a side slip. Another factor is the dihedral angle of the wing. What happens is when the aircraft sees a positive side slip, the local angle of attack on the windward side, that is, this were your wing. Let's see, is a positive side slip. This angle beta introduces, if there is a dihedral, it increases the local angle of attack. The normal component of the velocity increases the angle of attack by a small margin, but it does increase the angle of attack on the windward side, on this wing. So the lift produced on this wing is more than the lift produced on this wing. Again, it tends to produce a rolling moment. Okay. Another component is the sweep angle. Okay, this was not the dihedral, that was sweep angle. Similarly, the dihedral and the sweep both increases the angle of attack on the windward side. This is the windward side. Okay, this is the windward side. The wing that faces the wind. So it introduces a slight increase, a delta. There is a delta alpha in both the cases, which is proportional to this angle, side slip angle beta. So it increases the lift produced on the windward wing and decreases the lift produced on the leeward wing, which causes a negative rolling moment. Okay. Next case is the cross flow around the fuselage. I'll come to an image a little later. We'll discuss this point just in a while. The next point was the location of the vertical tail in relation to the CG, which is what is shown in this diagram. So if your vertical tail aerodynamic center is above the CG, it introduces a rolling moment. Cross flow across the fuselage was this point, which is seen in this figure. So for a high wing, low wing, we've seen several times why it contributes towards stability. So this cross flow across this fuselage also makes the angle of attack locally larger and smaller depending on the high wing, low wing configurations. Okay, so this again introduces a rolling moment. So the component that the fuselage sees is this V infinity sine beta, and it introduces a rolling moment, the flow across the fuselage. Okay, so these four quantities contribute towards inducing a rolling moment when the aircraft is subject to a side slip. I just mentioned this point for the sake of completion. We discussed adverse yaw, so I'm just discussing this. Okay. Okay, now we'll go over to the questions. Which of the following statements are correct? Airplane with higher wing loading has higher stall speed. A low wing with dihedral contributes towards longitudinal stability. A high wing contributes towards lateral stability and longitudinal instability. Winglets contribute towards minimization of wingtip vortices and thereby induce drag. Which points do you think are right?
A and B are right.
A and D are right. Let's just discuss it. So stall speed. What was the equation for stall speed? Under root
2W upon rho S CL max.
PL max.
We can write W by S. is the
Huh,
correct.
yeah. So this W by S, when we increase this wing loading, it has a higher stall speed directly proportional. And low wing with high dihedral, we just saw that it contributes towards lateral stability. Okay? So lateral, not longitudinal stability. A high wing contributes towards lateral stability, yes, and longitudinal instability. Now in the previous class, we had seen that if we had a high wing configurations, so if you have this as your fuselage reference line, and you have a high wing, the lift is produced here, the drag is produced here. This is the CG. So the lift contributes towards destabilizing. Drag also contributes towards destabilizing for a high wing configuration. If it is a low wing configuration, the lift continues to be destabilizing, but the drag contributes towards stabilizing. But the problem with this equation is that you cannot say that it has longitudinal instability. There is a small component that contributes towards it. But you cannot say that it contributes towards longitudinal instability because the drag encountered here is minimal when compared to the lift. Okay, The lift associated with both the high wing and the low wing already contribute towards instability. So high wing especially does not make such a great difference so that you can say longitudinal instability. Okay. The next point was winglets contributes towards minimizing of wingtip vortices and thereby induced drag. What were winglets? This was your traditional wing. When the airflow came from below and the airflow from above met at the wingtip, it introduced vortices. So if you had like a wing this way, it had vortices that traveled along the wake of the flow and contribute towards an induced drag. Now to smoothen out this interaction at the tip, you introduced winglets. Okay, so what happens is it gradually, obviously at the point where it means there will be some vortex generation, but since you're moving it gradually, there is smaller vortex generation there. Okay, and you're minimizing it towards a tip, not over an entire edge. So the vortex generation is minimized and the induced drag is reduced. Correct answer is both A and D. Okay. Which of the following statements are true for a typical flight profile for quadrotor aircraft and fixed wing aircraft? We had discussed this question, I think, in the second or third session. So what is the correct answer?
First option.
First option. Okay, so it says for a quadrotor, thrust by W is greater than or equal to 1. For a fixed wing, it is less than 1 because thrust is not what compensates the lift. Okay, so it's the compensates the weight. So lift is what carries the weight of the aircraft. So that is understood. For a quadrotor, if thrust by weight is equal to 1, what does it mean? If thrust by weight is equal to 1 for a quadrotor, what does it mean?
That thrust balances all the weight of the quadrotor.
Yes. So what is that condition called?
Hovering.
Hovering, yes. And what happens when it is greater, when the thrust by W is greater than 1?
Then it will move up or do side any maneuver.
Yes, so move up or take off or anything, okay? Or move up, yes. Climb. Okay. So these two conditions are encountered for the quadrotor, where if it is equal, if the thrust equals the weight of the quadrotor, it is hovering. It remains stable at a particular altitude. And if it's greater than 1, it increases the altitude, okay? For two different aircraft, a motor glider and a surveillance aircraft, the PS to W ratio and the L by D ratio is given below, where PS is shaft power. For a steady climb at speed 100 km per hour and propeller efficiency 0.8, what is the rate of climb for both configurations? How do we proceed?
Then we will start with the formula for rate of climb.
Okay, which is?
Power available minus power required upon weight.
Okay. Yes, you're right. Next. What is the power available?
Efficiency
I think V infinity
power
into
shaft.
thrust.
Can one of you speak? What did
Propeller efficiency multiplied by the power of the shaft power.
Power at the shaft.
Yeah, so it'll be shaft power into propeller efficiency, right?
Yes, ma'am.
Yes.
Okay, so I just substitute that here. PS by W minus PR was what? Power required is what? What is the power required?
V infinity
Okay.
into weight upon L by D.
Okay.
Something like that.
Isn't this just thrust?
You can write that thrust, right?
V
So
infinity into
thrust
thrust.
equals
Just
that.
thrust required. Right? You're right. It is TR is weight upon L by D. You're right. That was right. Right? I just replaced that W by L by D with thrust required. Okay.
Yes, ma'am.
Yes.
W will cancel out. And
Yes.
V infinity upon L by D will remain.
V infinity upon L by D. Exactly. So this will be PS by W into NS minus V infinity upon L by D. Okay. So I'll just write these down. I'll do it for the first one. PS was 7. Efficiency is 0.8 minus V infinity. Yeah. So here V infinity is given in kilometer per hour. We need to convert it. 1000 by L by D is 12. How much was this value?
Fourth option, ma'am. 4.67.
0.67. Okay. And what was asked? Right. Okay. Why did they say use small angle assumption? Where have we used this assumption?
Because in climb, ma'am, lift is greater than the weight.
Exactly. So the small angle assumption is you're assuming lift to be the weight, assuming small climb angle, right? So that is where we use the small angle assumption. Okay. With increase in wing loading, the corner velocity of an aircraft will
Increase.
increase. So all kinds of velocity that we've seen, all of them are directly proportional to wing loading. So what is this corner velocity?
Speed in a turn, we can say.
I didn't get you. Can you come again?
Speed in a turn.
Speed in a turn. Okay. Okay. So I'm sure you're aware of this VN diagram, right?
Yes, ma'am.
This is the corner velocity. What limits? So this shows you the limits that are imposed on the velocity. What limits do these curved lines impose?
Load factor.
Think about it. Think about it. What is the first limit that we impose on velocity? What comes to our mind immediately?
V stall.
V stall, exactly. So this is the positive and negative stall limits. And these are the structural limits. Structural limits, okay. So this corner velocity is, you can say it is the maximum, it's the velocity required to pull out maximum G maneuvers. So max G maneuvers. So the velocity required to pull off these maneuvers is the corner velocity. Okay. And they're represented by this equation where Nmax is basically L by W, which when it's maximum, it corresponds to the maximum G maneuvers. Okay. So the rest of the equation is similar to V stall. Only this Nmax component is introduced because you are no longer in steady level flight. You are pulling up or turning or any of those maneuvers. So it is the velocity that corresponds to the maximum G maneuvers. So that is one limit that we impose. Okay. Then, which of the following option is not correct? Velocity at minimum power and velocity at minimum thrust are same. Are they same?
No, they are not.
So that is not correct. At equilibrium, net moment about CG is 0.
Yes, that's why it is called equilibrium.
So we define equilibrium as sum of the moments and sum of the forces are 0. Airplane with higher wing loading has higher stall speed. We just saw it in the first question. It is true. At aerodynamic center, pitching moment coefficient remains constant irrespective of angle of attack. Again, by definition, that is true. So the only option that is not correct is the first one. Okay, let's just go over why it's not correct. Well, at minimum thrust, just recalling from the first lecture, CD naught by K and CL at minimum power is 3 CD naught by K. CL is changed, velocity also will change. Hence, the velocity at minimum power and minimum thrust are not the same. Okay. For a propeller aircraft at maximum range, what will be the wing loading? Given CD naught is 0.02, aspect ratio, efficiency, Oswald's efficiency factor, dynamic pressure Q. How will we start with this? How will we start with
We
this?
can calculate CL.
Let's calculate CL. CL is
For maximum range, it should be under root CL CD naught by K.
exactly. So we will write that PD naught is 0.02. K. What was K?
1 upon pi EAR.
Six. Mass spectral ratio is 8. What is this value? What is this value?
0.036.
Are you sure? Just somebody else just cross check this value. Okay, let's just proceed with this value. Just everybody just try to cross check this value and let me know if it's correct. Okay, then how do we proceed? We need to find out wing loading. How do we proceed? How do we proceed? What is the equation for
We knew the Q. So Q W by S will be equal to Q.
W by S will be equal to Q?
Q into CL max.
CL max.
Not
CL.
CL max, the CL. CL.
Yes. So how did we come with this equation? Can somebody else tell me how did we come to this equation? This is the right equation. How did we come with this? We have 5 other participants. Can someone tell me how we came to this? What is the lift equation?
Ma'am, lift equation is 1 by 2 rho v square CL.
V square SCL, right?
SCL. Yes, ma'am.
So this is Q. And if you take lift equal to,
Yeah.
you will have W equal to Q SCL. And from there, we have W by S equal to QCL. We'll just substitute the values here. Q is 39.2 and CL we calculated as 0.036. What is this value?
Ma'am,
Yes.
there is a correction for the CL term, ma'am.
Okay. Yes, tell me.
It is 0.55.
And answer should be first option.
Okay, answer should be.
0.5.
This is 0.5, right?
55, yes.
So when you substitute that here, you get 21.5. He's right. So it is the first answer. Let's try going to the next question. Okay. For a propeller aircraft at maximum range, okay, this is the same question. I just put this up to see why CL at maximum range is CD naught by K and CL at minimum power is CL 3 CD naught by K. Maximum range for a propeller aircraft is minimum thrust, and for a propeller driven aircraft, maximum endurance is the minimum power. It is the reverse for a jet engine. Okay, we have discussed this in the first 2 sessions. Does anyone remember why it's reversed? Why are these 2 conditions reversed for a propeller and jet? We had discussed this with the help of some graphs. You try recalling. So do you remember thrust versus velocity and power versus velocity? You remember these graphs?
Yes, ma'am.
Okay, so
For
tell
jet
me how
engine, I
this
remember
varies.
that. For jet engine, it remains almost constant.
Thrust, right?
Yes, ma'am.
Yes. And for propeller,
It decreases with increasing velocity.
and the power.
The power available increases, then starts decreasing, ma'am.
This is for jet or propeller.
Propeller, ma'am.
Something like this. And for jet,
For that, the power will start increasing, ma'am, as the velocity increases.
okay. Okay. So next class, and just look into these two graphs for these two conditions. So thrust versus velocity and power versus velocity for jet and propeller. Okay. So these two graphs, 1, 2, for these two types of aircrafts, and try to tell me why these conditions are reversed. Okay, we had discussed this in the first, I think, second lecture. So just try to come up with a reasoning as to why this is reversed. Okay, let's move on to the next question. Okay, what should be the load factor if the lift coefficient is designed as 2.1 and the aircraft is operating at a dynamic pressure Q as 20 Pascal? Given that wing loading is 12. This is similar to the first question. How do we go about doing this? How do we start?
Q into CL equal to W by S.
Okay. And how do you, okay. So they've asked you to find out the load factor. Load factor is what is to be,
N times W it will become.
okay. So CL is given to you and Q is given to you and W by S is given to you. Okay. So what do we do with this equation?
M, it will be N times W by S.
Yes, N times W by S. How did we come to that? We did lift equal to NW. Our original equation is this, but since we have an lift equal to NW load factor, we get this. So what is N? N is Q into CL by W upon S. Q is 20, CL is 2.1, and W by S is 12. What is this value?
2.5.
Sorry?
3.5.
3.25. Okay. So the load
3.5.
3.5. 3.5. Okay. So that is the load factor of this question. Now, what is meant by airborne distance? Is it the distance between takeoff point and the point at which screen height is cleared? Distance between liftoff point and the point at which screen height is not cleared? Distance between liftoff point and the point at which screen height is cleared? Or difference between takeoff point and the point at which screen height is not cleared?
Ma'am, I think so. Option A, ma'am.
So, what is screen height?
Ma'am, it is a minimum height at which an aircraft should able to reach the standards given by the aircraft committee, ma'am. Aircraft authorities, regulation, safety regulators, regulations, ma'am.
Okay. Okay. So let's just look at the takeoff flight profile of the aircraft. So it starts with V equal to 0. Then the first condition, first speed that it encounters is Vs. Vs is what is Vs? Vstall.
Vstall.
Vstall. So the first check is that it should cross above Vstall. The velocity should be greater than Vstall. Next condition that it is imposed upon is VMC. What is VMC?
Minimum control.
And what is that?
The speed at which the rudder, we can say it is functional.
Rudder is functional at all speeds, right?
No, ma'am, it isn't. But it won't be able to control the aircraft totally because it needs some air, some amount of Q pass through it so that it can. I mean, I know for Boeing 737 it is 80 knots for it to perform, to become active, so that it can control the aircraft on the ground. Else, we need to control with the nose wheel to maintain the center line of the runway.
Okay. So I'm not sure about that, but what I have read or I have studied is that if an engine fails, for the rudder to control it completely, for the rudder to compensate the yawing motion that is generated due to a failed engine, this is the minimum speed required. But it kind of makes sense that what you said is also similar to it. Okay. So let me just write down what I have learned. It's if one engine fails, this is for a multi-engine aircraft. If one engine fails, there is a yawing motion. So at this point, if the rudder has to completely compensate the yawing motion. Yawing motion. So the speed at which the rudder is able to completely compensate the yawing motion is VMC. But what he says is that at which it becomes operational, which I think amounts to the same thing. Okay, let me look into that again. Okay. So after that, we encounter V1. What is V1?
Decision speed.
Sorry?
Decision speed.
Decision speed. What does that mean?
I mean, I know from a pilot's perspective that he takes his hands off the thrust lever. That from now on he have to take do the lift off for the aircraft. He have to take off. Or we can also say at this point we can apply brakes so that the airplane can stop till the end of the runway.
Yes, that is the correct answer. So depending on the length of the runway, at this point, the length of the runway is sufficient to perform takeoff. It is also sufficient to abort the takeoff, right? So due to some reason, if he wants to abort landing, it has to be at this stage. So there is sufficient runway left for you to complete the takeoff. There's also sufficient runway left for you to abort the takeoff. Okay, so that is the decision speed. You're right. Decision speed. Next, we have VR. What is VR?
We rotate,
We rotate. And what is that?
at which then the pilot gives elevator input so that the nose wheel will come off the
Starts
ground.
rotating. Yes. Starts pitching. Correct. And next is VMU. What is that? Here,
Not sure about that, ma'am.
okay. Here it starts rotating. Here MU is minimum unstick.
Unstick velocity. Yes.
Minimum unstick. Any what does that mean? Any idea?
It is the speed at which the undercarriage, the back wheels haven't unsticked yet. But after just passing this speed, the undercarriage will also come up.
Yes. So what it is that if you were to take off at this speed, the undercarriage would just touch the runway. So you need to take off at a slightly higher speed, which is the V liftoff. Okay. And V2, what is V2?
It is the speed at which if one engine fails, then we can take off at this velocity V2.
Okay, so it
We-
is even with a failed engine, the amount of velocity required to clear this screen height, 35 feet. Screen
Yes.
height is nothing but an imaginary obstacle height that we keep there. Like he said, it is governed by the aircraft regulatory bodies. So this height, which it is required to cross. Okay, so I think the options are a little bit ambiguous. Takeoff and liftoff, pretty much the same thing, right? So
Takeoff is from the starting point. Liftoff is the point at which the aircraft is no longer on the ground.
okay, yes, you're right. You're right. So which would be the airborne distance? would just be this distance, right?
Lift off from V2, yes.
So it will be this. Okay. Okay. And what about the total takeoff distance? Will it be airborne distance
A
plus
and B, sum of A and B. sort of.
sum of A and B? Okay. Correct. Okay. Which of the following is not a type of flap used in aircrafts? What are flaps?
Ma'am, flaps are high lift devices, ma'am.
Yes. So which of the following are not a type of
Fourth
flap?
option, dorsal.
Dorsal, ma'am.
Dorsal.
Dorsal. What was associated with dorsal? What did we have?
Dorsal fin we have.
Yes. And what was its purpose? What dorsal fin
To
was
increase
The
the
drag,
stalling
ma'am.
angle of the vertical fin.
to increase the
Stalling angle of the vertical fin.
yes. So this was your traditional vertical tail, and then you had a dorsal fin here. So it increased the range of operationality of the vertical stabilizer, vertical tail. So let's just have a look at the different types of flaps. You have plain flap. Plain flap is nothing but the trailing edge of the wing cross section is bent downwards. Then you have the split flap, where the upper surface of the wing remains the same, just the bottom surface is split and bent down. What do you think are the differences between this and plain flap and split flap? Like operational
The
differences?
upper surface of the uh, aerofoil in the split flap is pretty much maintained.
Yes. So what benefits or disadvantages do we have?
I know about disadvantage that it increases wave drag,
Yes.
but the advantage we can say that flow will remain almost stick to the surface till the end of the airfoil.
Exactly. So boundary layer separation is delayed. Here it will not stick towards till the end. Increases drag. So this is more often used, split flap is more often used as a spoiler. If it's completely deflected, it is used as a spoiler. Then we have slotted flap. What is a slotted flap? Where the trailing edge of the wing moves behind and then bends. So there is a gap here, which allows the air to flow over it. What is the benefit or disadvantage of this?
Re-energizes the boundary layer above the flap.
Yes, correct. So the boundary layer separation is delayed. So you have flow that is maintained over the surface, and it also increases the camber, which is one of the main purposes for the high lift devices. Then you have the Fowler flap. What happens here is that this is the intermediate position. So it first increases the chord and then it is bent downwards. So it increases the camber. So what is the benefit of this as opposed to the slotted flap or the split flap or any other configuration?
It increases CL further more than any
This
other.
is CL further, yes. So in this case, the chord is also increased. The camber is also increased. Okay. And then you introduce several slots over the Fowler flap to introduce this boundary layer re-energizing concept. So it increases it further. So this increases, it has combination of both Fowler and slotted flap. It has the benefits of both the configurations. Okay. What other high lift devices are there?
Slats are there. Slats or slots.
Slats or slots. What are slats or slots?
These are leading edge devices, similar to almost similar to flaps.
Okay. And what do they do?
They also increase the CL max.
And what is the difference between slat and slot?
And just maybe we can say the positioning that flaps are at trailing edge and slats or slots are at the leading edge.
Okay, the trailing slots are basically the slotted flap. So the leading edge ones are called leading edge slots, yes. But as far as I know, I could be wrong, but slats are permanent, they remain fixed, and slots or slats it's vice versa. Just look into that.
Actually, ma'am, both of these can be retracted as well. Either it is flat or slot. Because slot, I have seen some pictures of both of these. So
Hmm.
slats are extended but are attached completely with the upper surface of the airfoil. Means there is no gap. But in
Okay.
slot, there is gap between the slat surface and the main aerofoil starting.
Okay. And both are retractable?
Yes, ma'am.
Okay. Okay. Thank you for the information. I was not aware of that. Okay. Okay, let's go to the next question. An aircraft is flying with a wing loading of 50. So what is given is wing loading is 50 and maximum CL as 2.4. Okay. If the density is 1.225 kg per meter cube, then what is the takeoff velocity? V takeoff. This is fairly simple. How do you proceed?
First, we have to find out the V stall, ma'am.
Okay, and what is the equation?
Under root of 2WS by rho CL max.
What? Let's try to do this.
Ma'am, I got the answer.
Yeah, okay, then I'll just go ahead with this. Into 2.4. What is this value?
Option D.
Okay, let me just proceed with this. What is this value?
Second option, ma'am, 6.41. No, sorry, ma'am, sorry.
This value is 5.832.
5.832.
Two. And the takeoff is just multiplying it by 1.1, which is 6.4. Yes. Correct? Is this what everyone has got?
Yes, ma'am.
Somebody had said fourth option. Did you figure out the mistake? Let's move on. An aircraft is cruising with a lift coefficient of 2.5 and a thrust loading of 0.6. Find the drag coefficient of the aircraft. This? Proceed with this.
By the thrust formula, ma'am, T by W, W by T equals to L by D. Or vice versa, we can say W by T by W equal to 1 upon L by D.
on L by D. So what we have defined is the drag coefficient. So A by W is 1 by CL by CD. That we have CD equals T by W into CL, right? Okay. So T by W 6 into 2.5, which is
1.5.
1.5.
where are the others? Why are they not responding to any of the questions? There are at least a few others. Try to respond from the next question, okay? Okay, so let's move on to the next question. For an aircraft in flight, wings produce a lift of 25,000 Newton. The drag of the aircraft is 1 order of magnitude smaller than the lift. Find the jet engine's output for a steady flight at 500 km per hour. So what is given to you? Wings produce a lift.
We have an L by D,
Drag?
2500 Newton. 10% of it.
Exactly. Then we have flight velocity. And they've asked you to find jet engine's output, which is what? Thrust. Right?
Yes, ma'am.
So how do we go about doing this?
thrust equals to weight upon
Since
L
the
by
options are in milliwatt.
V infinity into
Yes, I'm sorry.
power.
Can you start again?
Power upon V infinity.
Okay,
If we
since
don't have
are
power
in
in general.
watts, we need to find out watts. We need to find out the power, right?
Okay, we need to find power. It is V
Yeah, yeah.
infinity into T.
Yes,
Thrust is equal to drag in level flight.
exactly. So are the others following this? How do you
Ma'am,
Yes,
tell me how do you find out the power?
thrust into velocity.
Okay, and how much is this? Thrust is
D by L.
D. So 2500 into velocity is
We need to convert it into meter per second.
exactly
138.888.
okay. What is the final?
And it will be D by L, right?
Sorry, I didn't get you. What?
Thrust into velocity, right? Thrust will be D by L. 2500 by 25,000.
Thrust will be just drag, right? So in the steady lift, it will be thrust equal to drag, correct?
Okay, steady. Got
Yes. So how much is this value?
Third option, ma'am.
Okay.
0.347, around 0.37 megawatt.
347 megawatts. This is the correct answer. Okay. So is everybody else also following? It's just thrust into the
yes,
velocity
ma'am.
V infinity. Okay. So we saw two questions where the value was given in kilometer per hour. You need to keep this in mind that your value should always be meters per second. So you must always convert it to meters per second. Okay. For a transport aircraft, the maximum allowable load factor is 6. Find the thrust loading if aspect ratio, Oswald's efficiency factor, and CD naught are given. So what is given is Nmax equal to 6. They've asked you to find out thrust loading. How do you proceed with this?
We can get CL by CD ratio.
Okay, how do we get CL by CD?
For thrust loading, should we use minimum power condition?
So it says it is maximum allowable load factor. So it is N is L by W, and that is thrust by weight into what will it be? Lift by drag, right? Yes. So in this condition, we should increase both P by W and L by D. That is when you get N max. You must maximize both. Correct?
Yes.
Yes. So what will CL by CD be? Let's start with CL. CL was
Under root of CD naught by K, ma'am.
CD naught by K. So what will it be? CD naught is
Under root of CD naught by AR into E, ma'am.
what
By
was
AR into E.
K was 1 by pi EAR, right?
Yeah, ma'am.
So it will be pi EAR. It will be 0.01 into 5 into 0.7 into AR is 8.5. How much is this value?
Point 432.
Oh, just a minute. Point 432. Now we were supposed to find out CL by CD. So CD is, how do you find out CD? What was the drag polar equation?
It will become twice of CD naught.
I'll just write it down for completion. V CD naught plus KCL square. That in this case, for this particular case where L by D is maximum or CL by CD is maximum, which corresponds to, for a propeller aircraft, CL by CD maximum corresponds to maximum range, right?
Yes, ma'am.
Okay, so here you have 2 CD naught, which is 0.02. So your CL upon CD will be
21.6.
21.6. Okay. Next, how do we proceed next?
We will just reverse this ratio and multiply it with n.
Okay, yeah. So we'll just substitute in this equation. You need P by W is equal to N max.
0.277 second of.
So that will be 6 by 21. What was the answer? 0.277.
Yes, ma'am.
So how do we proceed with this question? First, when you see this maximum load factor or anything like that, you start with N equals to L by W. And you substitute the values here. So you have L by T by W. They've asked you to find out T by W. So you write it in those terms. T by W into L by D. And since it says N maximum, both these quantities have to be maximized. So ideally, the question should have said find the maximum thrust loading, because for maximum allowable load factor, you have maximum thrust loading. You also have L by D max. L by D max corresponds to CL value of root of CD naught by K. So you substitute that ratio here. You already have your N maximum and you can find out the thrust to weight. So this question should have said find the maximum thrust loading. Okay, let's move on. For the same question, what is the wing loading? What is W by S? For the same question. How do we proceed? Because I think one of the questions we had already done this. How do we proceed? Somebody else tell me this time. How do we find out W by S? How do we find out W by S? We just done a question on along similar lines. How do we find out W by S?
CL max by load factor.
What was it? CL max by?
Load factor.
Okay. So what is the value? CL, we had found out CL to be 0.432 by load factor is 6. And what is the value?
Point 0.072.
That is not one of the options. Where have we made the mistake?
No, ma'am, in this formula, pressure is also included, right? So that's not given.
Sorry. Okay, let's just start with the lift equal to weight equation, proceed from there. So you have lift equal to NW. And here you have half rho V square SCL equals NW. And you need W by S. So you have W by S is Q CL upon N, right? They should have given a Q.
Yes,
Yeah.
ma'am.
They should
data
have
is
given a
missing.
Q.
Missing.
Okay, let's just take some V equals 100. Meter per second and proceed. So there should have been a Q. That is my mistake. It should have a velocity. Equals 100 meters per second. Okay. So, Q is half rho take rho as mean sea level. So that is 1.25 into 100 square. CL is 0.432 by n is 6. How much is the value?
445 it is.
So since I've just taken a random value, it will not match any of these options, but wing loading we just calculated was rho v square CL upon n. Okay. Okay. Now we'll just we'll just go over this aerodynamic center calculation and we'll try a new structure. So for this configuration, your aerodynamic center was here. Okay. So this is your mean chord. C bar was mean chord calculated by this formula, where lambda is the taper ratio given by a chord at the tip by chord at the root. And so this is X MAC and this is Y MAC. Okay, so this was your aerodynamic center. Now let's try it for a different shaped wing. Let me just draw it. It's tapered about the quarter chord axis. Okay. Okay. This quarter. Okay. So see this angle is given to you as 4.3 degrees. You have the root chord CR and CR is 0.6 meters and you have this distance to be 2 meters. 2 meters. And this small distance is 1 meter. Okay. Now find AC. So how do we proceed with this? How do we proceed? First, you split it into 2 sections.
A rectangular part and 2 frustum.
So let's take this as 1 and this as 2. Now let's proceed to find it out for 1. So for 1, let's start with area. What is the area?
2 into 0.6.
2 into 6, which is
1.2.
okay. So we'll take only towards one side, okay, and then try to find out the aerodynamic center on this side, okay. So if it is just like 1/2, okay, so we'll just take this. The mean, so we'll just take this half I meant, okay. That makes it easier to find out the aerodynamic center on one side, to find out the Ymac, okay. So the mean aerodynamic chord will be somewhere here. So we'll just have to take this area. Let's try with different color. This and our second area will be we'll find out the areas of these two sections. So it'll be 1 into 0.6 will be 0.6 meter square. Okay. Next, let's find out what will be the taper ratio will be
1.
1. Then aspect ratio will be 1 square by S1. Just this small blue section. Okay.
1 by point.
B is 1 by 6, which is then let's find out the mean aerodynamic chord of just the rectangle. What was the equation? 2 by 3 into CR into 1 plus lambda square by 1 plus lambda. In this case, lambda is 1. So you have just CR. Right? So that's just 0.6.
0.6.
Now let's do it for the second. This one in purple. So for the second one, you have S2. What is the area? Area of a trapezoid.
Half into 0.6 plus CT.
Yes. Half into point.
Half into
CT
0.6 plus CT.
0.6,
in bracket. CT plus 0.6.
0.6 plus CT
Into
into 1, right? So the span is 1.
Yes.
Okay. How do you find out CT? How do you find out CT?
We
Taper
have the
wish.
angle, ma'am.
Yes. So this is CT. Let's try to find it out. How do you find it out? How do you proceed? How do you find out? It is based on the angle, but like try to figure it out.
Cos of 40,
I'm sorry, your voice completely, I lost it. What did you say?
it will cos of 4.3, I think. Yes.
Cos of 4.3 is what?
I guess we can do tan of 4.3 equals to the upper height difference divided by 1. It
Let's
won't be CT. Yes, this distance from this to the
be this, right?
yes distance.
So I'll just take it as, let's take it as some L. So that will be L by 1.
L by 1. Yes.
So how do you find out CT from this? So CT plus L equals CR, right?
Yes, ma'am.
Is this right?
Yes.
Yes.
Okay. So you have CT equal to CR minus 2L. That is what is
0.152L is coming. 0.6 minus 1.15. 0.6
6
minus 0.15.
1. So what is the value?
0.45.
Okay. So now we substitute this into this equation. How much do you get? How much is the value?
Point 5025.
5025 meter square. Okay. Next, what do we lambda? Just put this separately. Lambda 2 CT upon CR. How much is it? CT was 0.45 by CR was 0.6. How much is this value?
0.75.
Okay.
Ma'am,
Yes.
it is 525 for the S2.
Okay, just a minute, just a minute. We have made a mistake here. So it's tapered about the quarter chord. So this is not equal to L. Right?
Yes, ma'am, then it should.
So how do we find out CT? So this equation is not right. Let me just write that down. So this is not right. Let's try to find out how to do it. It's tapered about the quarter chord. Does that give you any hint? Try to work on that. It's tapered about the quarter chord. So if this
Can be
is
12.
sorry,
The upper part is considered as L. So downward can be 12.
why will it be
Right.
L? Will it be 12? I'm not sure. I'm just thinking aloud.
No, I'm just assuming it like it has told the quarter part, right? So if we are considering the above as L, the down can be 12.
Okay, let's try to proceed with that calculation. I'm not sure. We'll just try doing it. Okay. So it'll be CT plus 2L plus L equals CR. This is what you said, right?
Yes.
Let's just see. I have the CT value with me. Let's just see if it matches. Okay, CR minus 3L. Will it be? How much was this? Tan 40. This was 0.375.
0.375.
Okay, 0.6. 0.37. No, it doesn't match. So what I have done when I was solving this is that, just write that down. Okay, so now CR by 4 equals CT by 4 plus L. This is what I have done. So what it essentially says is that just draw that. Okay. So this small distance is CT by 4 because it tapers about that axis. Okay. And this distance is CR by 4. So CR by 4 equals CT by 4 plus L. Does that make sense? Let's try writing it in a different color. So you have this tiny distance is CT by 4 because it's tapering about that axis. And you have this quarter chord point at root to be CR by 4. So this is CR by 4. So if you CR by 4 is the one in yellow, and the one in green is CT by 4. And then you have your small L, which is this tan 4.3. Does this make sense? Yes. Does it make sense?
Yes.
Yes. Does anybody have any questions here? This one did seem intuitively right, but it is not giving the same answer. I will look into it. I hadn't thought about this approach before. This is what I had done to solve it. But this approach makes sense, right? So the problem with this approach is that this angle could be anything. It need not be double of 4.3.
Yes.
So that is why I think this is wrong, but I will.
It was just raw assumption.
Your voice is breaking. I'm not catching you.
No, I told it was just a raw assumption. It could have.
Yeah. Okay. But it did seem intuitively right. I will look into it. But this approach is, does everyone agree with me with this approach? This one?
Yes.
Yes, ma'am.
So let's proceed with this. So CT by 4 is CR by 4 minus L, which gives you CT is CR is 0.6, right? CR was 0.6 divided by 4 minus L was 0.075 into 4. Gives me 0.3. Is everyone getting 0.3? Does this make sense? 0.3. Is everyone getting 0.3?
Yes, ma'am.
Okay. So let's substitute that value here. So it will be 1 by 2 into 0.6 plus 0.3 into 1. What is this value?
0.45.
5 meter square. Okay. Okay. So let's move ahead. What is the next value? Lambda 2. Lambda 2 is CT upon CR. What is this value? CT was 3 divided by 0.6. So it was just 0.5. So what was the equation for C bar, mean aerodynamic chord of just the purple part? What will it be? Let's just write this down something else. So C bar 2. What was the equation? It's 2 by 3 CR into 1 plus lambda square by 1 plus lambda. That comes to, can you tell me the value? How much is this value? How much is this C2 value? How much is the C2 value? Am I audible? Are you guys with me?
Yes, ma'am.
Yes. Okay. Just well, calculate this and let me know. Lambda 2, this is lambda 2. So this should be CR2. In our case, CR1 equals to CR2. So it's the same. So can you tell me what this value is? It's a simple calculation, just let me know. Write it down. 253.6.
0.466.
Just complete this now that I've started it. Six. Okay. Now we have got the aerodynamic chord, mean aerodynamic chord of this section and of this section. Okay, so we need to find its something like this. So this is C2 bar, and this is C1 bar. So we need to find out the mean aerodynamic chord of this entire section, the purple section plus the blue section. Any ideas as to how we will find out that? We have their individual mean aerodynamic chords. How do we find out their overall aerodynamic chord, mean aerodynamic chord?
Ma'am,
Yes.
can we just do C bar 1 plus C bar 2 by 2?
We just do that. It is an averaging. You are right about the averaging aspect of it, but can we just take C1 plus C2 by 2? In that case, so let me just take another section. Let me try to draw this again. Okay, so am I audible?
Yes.
So our mean aerodynamic chord here was C1 bar, here was C2 bar. Okay, so if I say suppose the overall C bar is C1 bar plus C2 bar, then if I had a different cross section here, if I had a triangle, then it would be somewhere here. Then again, it will be C1 plus C2 bar. Will it be like that? Will the shape of the wing have no effect on the averaging?
It will do have, ma'am.
How do we bring about that aspect into this averaging? It is an averaging, but you need to add some terms to this averaging. This is what you say. What terms do we add to this averaging technique? This is a linear averaging technique. What terms do we add to it to make it little more realistic? You think about it? Okay, so how do we find out? We had done the centroid calculations, right? So if you had some structure like this, and you had something like this, you had the centroid here, you had it centroid here. How did we find out the overall centroid?
Ma'am, we found out by centroid of the square plus the centroid of the hemicircle, half circle, ma'am.
Yeah, so centroid of the square is here, centroid of the semicircle is here. How do we find out the overall centroid of this entire structure, of this entire 2D shape? centroid, or if it's a 3D center of mass, how do you find out? How do you find out the centroid here? Centroid of the square is here. So if you take this is your reference X, this is your reference Y. So this is at X by 2, and this is at Y by 2. This is still, that is also X by 2. Not sure what this was. I'm not sure what the centroid value was, but what, let's just say it was some Y2. How do you find out the overall centroid?
Ma'am, centroid of the square plus centroid of the hemicircle by 2, no ma'am.
Was it like that? Overall centroid, let's just say X bar. In this case, X bar is X by 2, fine. Y bar was what? Centroid of the square.
If it
was
lies
Y.
on the diameter.
Centroid of Y square was Y1 bar. Centroid of circle, semicircle was Y2 bar. How do you find out the Y bar of the overall structure?
y2 y1 upon y1 plus y2.
Didn't it have something to do with the area? Was it not A1 Y1 plus A2 Y2 upon A1 plus A2? Was it not this? I'm not sure, I could be wrong, but this is what I recall. Isn't this right?
Ma'am, but why would area come here, ma'am?
Was it Y1 plus Y2 by 2? Let me just figure that out. Just give me a second.
Ma'am, because here we are just finding out the centroid.
Of the overall structure, yes. Just give me a second. Let me just Google it. So let me share this. I just did a quick Google search and this is what I came up with. So do you see this figure? Can you see my screen? Can you see my screen?
Yes, ma'am.
Yes.
Okay. So here you can see that so xi bar is the individual axis. So this is the centroid of the square. This is the centroid of the triangle. And centroid of the square is x1 bar. Centroid of the triangle is x2 bar. And y1 bar, y2 bar. So how do you find out the overall centroid? Was x1 bar a1 plus x2 bar a2 upon a1 plus a2, and y1 bar a1 plus y2 bar a2 upon a1 plus a2. Was it not like this? Do you recall this? Is this right?
Yes, ma'am, it should be.
Okay. You all studied dynamics and static mechanics and all of that, right? So centroid, center of mass calculation was there. what about center of mass? If it's a 3D, it's an object. How do you find out center of mass?
Ma'am, we do it by taking the distance uh, distance from the origin, ma'am. For example,
Okay, but if it's a combined structure, okay, so next class, I want you to tell me how do you find out the center of mass. So this is for a 2D, centroid is for 2D. Find out the equivalent for a 3D structure, okay? So now,
ma'am, the center of mass formula is xi mi by xi, ma'am.
xi mi by x.
Summation, ma'am. Summation of xi mi by xi.
Summation of xi mi by, will it not be mi?
No, ma'am, because xi is the distance, ma'am.
Center of mass. Okay, yes. My bad. Okay, so it will be summation xi. Yes, so you all remember this, right? So this was center of mass.
Yes, ma'am.
So it is a weighted average, right? So weighted average. In this case, also it's a weighted average, but since it's a 2D structure, we take the areas.
Okay, ma'am. Understood,
You have
ma'am.
to revise your centroid, center of mass calculations. Okay, let's get back to our
Yes, ma'am.
question. Okay, so in our case, what will it be for this case? What will be the mean aerodynamic chord proceeding along the similar lines?
Ma'am, it will be the centroid of the square into area of the square plus the centroid of the semicircle into area of the semicircle.
No, not this question. This one. Our wing, the aerodynamic chord, mean chord. How do we proceed along? Just think along similar lines.
Ma'am, C1 bar into the area of the square, ma'am.
Just S1. Okay.
S1 plus C2 bar into S2 by C1 bar plus C2 bar.
No, areas for that.
Yes, it should be S1 plus S2. Correct? Because we need C. We don't need the area. We need the weighted average of C. We don't need the weighted average of the area. Correct? Do you understand why it is S1 by S2 at the bottom?
Ma'am, I didn't understand clearly, ma'am.
Okay, so for centroid, it was A1 Y1 plus A2 Y2 by A1 plus A2. Right, so basically what you're doing is let's try doing it with dimensional analysis, okay? So what you said was C1 bar S1 plus C2 bar S2 by C1 plus C2. This is what you said, right?
Yes, ma'am.
Now let's take what is the dimension of C1 bar? What is the unit?
Meters, ma'am.
Meters. What is the unit of S1?
Square.
Meter square. So this is the numerator's unit. Denominator is C1 is, what is the unit?
Meter plus meter.
Meter plus meter. So what is the final unit? It will be meter square. Right?
Yes, ma'am.
So, but we need C1 bar. We need C bar, the unit of which is only meter.
Yes, ma'am.
So the denominator should have meter square.
Okay, ma'am. I understood, ma'am. Now I understood.
Okay. So this is the correct equation. This one. Okay. So let's proceed to find out the aerodynamic chord. C1 bar was 0.6. area was 0.6. C2 bar was, where was C2 bar? 466. S2 was 45. This one is 0.6 plus 0.45. What is this value? What is this value? Just calculate and tell me.
1.39.
0.3.
1.39.
0.3. Are you sure? I think I've made a mistake in my calculation then. Let me just try doing it again. Isn't it coming 0.54?
It's point. My mistake. 0.54.
So it's 0.54 meters. This is wrong. Okay, now that we have the mean aerodynamic chord, we have the length. This is C bar. We were asked to find out XAC. How do you find out XAC? How do you find out this? XAC, suppose this is your leading edge. Suppose your mean aerodynamic chord was somewhere here. Suppose this is the final value. This is C bar. This was C2 bar. So how do you find out this value? So the mean aerodynamic chord is at the quarter chord point, which is here. Correct?
Ma'am, on C bar, ma'am.
On C bar here. This is the aerodynamic chord, right? AC, aerodynamic center, my bad, aerodynamic center.
Yes, ma'am.
Yes. How do you, what is XAC? XAC is this. Let me take another color.
The quarter part of,
This is XAC, the one in blue, correct?
yes, ma'am.
Okay. How do we find out that?
Ma'am, C bar by 2 plus C bar 1 by 4.
C bar by 2. Why C bar by 2?
Ma'am, because here the line which you drew,
Yes.
it isn't exactly mid, ma'am.
It's at the quarter chord. The line is at the quarter chord. This is,
So, ma'am, should be that line which is horizontal, ma'am, on the half or the quarter of the C1 this C bar, ma'am.
I didn't get you. So what are you saying? XAC equal to?
Just can I just draw once and show you, ma'am?
Yeah, sure. I'm not sure how you're going to do that.
I said that, ma'am, you. Ma'am, so here I'm saying, ma'am, the line which is above, ma'am, just near the The first one, ma'am.
Uh,
The topmost one, ma'am, in blue one.
this one?
No, below this, ma'am, horizontal one, ma'am.
This one?
Yes, ma'am.
Yes.
So,
yes.
should we consider this quarter line or the line which is passing half of it, ma'am? The bottom one, just below it.
So the one, this red line that I've drawn is the quarter chord line.
Okay, ma'am. I was thinking it should be actually half, ma'am. Half of the entire
So I
aerofoil.
had mentioned taper axis as quarter chord, right?
I didn't see that, ma'am.
Okay. So taper axis is quarter chord, which is why we got this equation. Did you follow this?
Yes, ma'am.
Okay. So here taper axis is quarter chord. So what is XAC now? So since this is quarter chord. So what I mean to say is this is CT by 4. This is CR by 4. This is it is the quarter of every chord along the axis. Okay. So what will this line in blue? That is XAC. What will it be?
Ma'am, C by 4 plus C1 by 4.
Is C bar by 4 plus
C1 bar by 4. Because it lies along the quarter of every line
so
of the
C1
entire
by
CR, ma'am.
Yeah. So C1 by so this value is CR by 4, correct?
Yes, ma'am.
I'm not sure how to draw this. Draw this clearly. Chord. So this point x-axis would be what? It would just be CR by 4?
Yes, ma'am.
Yes, correct. So it will be just CR by 4, which is 0.15. Since it's tapered across the quarter chord axis, it will just be 0.15. I mean, it will just be CR by 4. Okay, is that clear? If it was tapered about any other axis, then the equation that you said would be true.
Yes, ma'am. I understood.
Okay, so is this question clear to all of you?
Yes, ma'am.
Yes.
Okay. So with this, we come to an end of this session. Does anyone have any questions? Any doubts, any questions?
Ma'am, I want to ask one thing, ma'am, for the exams conducted by NPTEL, ma'am.
Yes, yes, ask.
So in those exams, will it be theory or like give us questions and we have to solve them, ma'am?
It'll be just like your assignment questions.
Oh, so that means only MCQs will be there, ma'am.
Yes, yes, only MCQs. And you may have a few numerical answer type.
Okay, ma'am.
In the exams, you had numerical answer types, right? I mean,
Yes,
even
in this 8
Yeah,
sessions we have numerical.
yes. So these are
But
the
even
two MCQs and numerical answer.
but even numerical ones had the options. So what about an exam? Will we have option or we have to type the number?
it'll have both these categories, typing the number and the multiple choice questions. But I think for numerical answer, you will not have a negative marking.
Okay.
Ma'am, it's an offline exam, right?
I think so. Yes, yes, offline. Yes.
Yes, that's fine.
Any other questions? So
No,
I saw
ma'am, thank you.
questions on the forum saying that we need to share the problem solving sessions. You all have the link to the YouTube playlist and the drive, right?
Yes, ma'am.
Yes, ma'am, it is
Okay.
available.
Any other questions? Any doubts? Anything?
No doubt, ma'am. Thank you.
Okay. So then we'll end the session here. We'll meet again next week. Good luck with your exams, with your assignments. We'll end the session here. Thank you.
Thank you, ma'am.
Thank you,
Thank you very much.